is the input layer, this is the hidden layer, this is output layer. And the notation is yi is the output, vj is the hidden layer state, and xk is the input, kth input. And so if you give xk as input to this layer, then hjf is the total input going into the jth hidden neuron, and output of the hidden neuron is vj, which is g of hj of f, this quantity. Then vj's are then sent upwards to the output layer, and here you calculate the total input going into the output neuron, that is hi, hi of s, the second layer, and here we're using hij of f, which is first layer. So this is again linear sum of all the outputs of the hidden layer, right, going into this neuron. And then the actual output of the output layer is given by yi is equal to g of hi of s. Okay, so this is how you forward propagate the input all the way to the output and calculate the output. Now, how do you update all the weights? Because training means updating all the weights in such a way that the output error goes down, or ideally goes to 0. So this is output error, and if you take the error corresponding to the pth pattern, that is EP, right, that is given by this expression, that is output error, sum of the output errors of at each of the output neurons. So now let us calculate what is delta W S ij and what is delta W F jk. Okay, and the rule is always the same, it's just gradient descent. So if you do it for the second stage weights, that is WS ij, that is equal to, if you calculate the derivative, so you have, if you just take the derivative part, so actually you have to have like, you know, so this is just dou EP by dou W ij s, right? So that is half into 2 into di minus yi, here minus 1 derivative, this gives you minus 1. Then g prime of hi of s, it is right here, sorry. Times vj, okay, so right, so that if you regroup a little bit, half and 2 and half get cancelled. If you take use this equation, plug this into this equation, you get delta Ws ij is equal to eta di minus yi g prime hi of s vj. Okay, so what this is saying is, if you take a weight here, right, going from hidden neuron to the jth hidden neuron to the ith output neuron, the update for that weight consists of di minus yi. Di is the desired output, yi is the actual output. Take the error between the two, and times g prime of hi of s, which is also happening here, right, times vj. So you have some error related information that is available at the output end and the state information at the input end, vj. If you take a product of these two, that will give you the update for wijs. So that means something information available at output end times information available at the input end. If you multiply those two, you get the update for this connection. So that which is physically also quite plausible, right? You can imagine that given a real synapse, right, updates itself, changes its strength by using information available at the presynaptic and the postsynaptic terminals. This is only like, I'm saying it more like a hypothesis at this time, but we can look at some data of what happens in real synapses later. So basically, this update rule satisfies the locality principle. But things are not that simple when you go to the first stage of weights. So here, let us see what happens. So here again, if you want to extend this, delta W jk f. So delta W jk of f will be equal to again eta times dou EP by dou W jk of f. So let us look at the gradient. So dou EP by dou W jk of f will be equal to again half times 2 times 2 times. Now this earlier we had NO, the number of neurons in the output layer is NO. We had so many output error terms, di minus yi square terms. out of them, when we differentiated this whole summation using this weight with respect to this weight, then you can see that only one of these terms is dependent on this particular weight. Only the error at the ith output neuron is dependent on Wij of S, because this weight doesn't show up in the error for other neurons. So when we differentiated this entire expression with respect to this weight, only the di minus yi term shows up. Therefore, we had only di minus yi. We didn't have the entire summation over I. But things are different in this case, because if I take a bunch of neurons in the output, this is my jth neuron, and I'm calculating the effect of this weight, which is wjk, this is k, first stage. So my error is, output error is sum of errors available at all these things, that is my E. So if I'm calculating the effect of this weight on the output error, right? So this weight shows up, so this weight influences this state, this is Vj. Okay, so if you look at the sequence of dependencies, wjk of f influences Vj, and Vj in turn will influence all the outputs. Okay, so that is each of these, actually each of, so each yi for all I. Okay, and so therefore yi then influences EP. Okay, so all the yi's influence EP. So this is how the dependencies work out. So therefore here I have to have half times 2 times sigma di minus summation of I, di minus yi, okay, times minus 1 for this minus factor of yi. So then dou yi by you get dou yi by so we have to ultimately differentiate this with this. So before that we differentiate with respect to Vj, right? So dou yi by v and dou Vj means you have G prime of the output I, second stage. Okay, then you have second, right? And then you have W. So dou H by, then you have dou Hs I by dou Vj. So if you go back to this expression, okay, so dou Hs I by dou Vj, that will give you Wsij. So that comes here, Wsij times dou Vj by dou Wjk of F. Okay, so I just didn't want to put everything in one line, it will be pretty long. If you take this expression, dou Vj by dou Wjk of F, so dou Vj is given by this. So this quantity by this quantity gives you is equal to G prime of the H at this hidden layer, that's the jth hidden neuron. So Hj F times, to differentiate this with respect to Wjkf, so that gives you xk. If you put this whole thing together, you have this derivative is equal to, so again if you go back, sigma, I'll put this in brackets. So this is I di minus yi times minus 1 times G prime Hi of S times Ws, sorry, so Ws here and Hij here, there's a mistake here, sorry. Okay, and times G prime Hj of F times xk. So it's a pretty long product of lots of terms. It's a pretty complicated expression. Now the thing is, even if you plug it into this equation, you just get rid of the minus sign and you have pretty much same expression with an eta factor in the front. The point is, it's a pretty simple derivation. Now, if this is the final answer, right, something seems to be wrong because so we said that the backdrop algorithm was discovered by several people. Some Paul Verbos discovered it in the 70s, and then Parker, LeCun, and all these guys have discovered it in the 80s. So point is, what we have done to work out the backdrop rule, right, took us maybe 20 minutes. Okay, 2 half sessions or maybe half an hour. So what is such a big deal? I mean, why do we make so much drama about all these people discovering this algorithm? Because all that it requires is taking partial derivatives of a slightly complicated function. You need to make sure your indices are right and you're not messing up indices. Okay, so the point is, if this is all that they have done, it's not such a big deal. But what they have done is something more intelligent. And actually, there's a small problem with this expression, which is that let us invoke the locality principle. So we have seen that in the first expression for the update rule, update for these weights, it satisfies the locality principle. But let us look at the update for these weights, the way we have derived it. So to update a weight here, going from kth input neuron to the jth hidden neuron, I need di minus yi, this error term, from all the output neurons. Now, this connection and these neurons are very far from each other. In fact, this is an MLP, so at least they're one synapse away. But if you think of a much larger network, like a deep network, for example, which can have any number of hidden layers. In fact, MLP also can have any number of hidden layers, but typically when we say MLP, we kind of assume that it is a single hidden layer, but it's not necessarily true. So these neurons are so far from this, and interesting question which for biological plausibility is how does this synapse know about what is happening so far from here? It's a valid question, there's no answer. Mathematically it's okay, but if you look at it from a biological realism, it's terrible. That cannot be happening. Right, so you need these quantities, you need the G primes which are available here and so on. Even if you let go of all this, if you ask how does a neuron calculate G prime of HI of S, there's no answer to that. Probably it doesn't. Okay, that way the whole algorithm is somewhat simplistic or too artificial, right? But even if you invoke the locality principle, which is a much milder condition for you to take it as a biologically valid learning mechanism, yeah, this equation doesn't satisfy the locality principle. So people have recognized that when very very early on, and they said it is possible to redo these equations, these learning equations, in such a way that at every stage the update satisfies locality principle. How did they do that? So they define new quantities called deltas. Okay, so these deltas, there's a notation that they use, are like error terms. What are the errors? So at the output layer, error is simply di desired minus out minus actual. So here they also multiply this G prime Hi of S. Okay, and they'll tell you in a minute why it is necessary mathematically. And they define this as delta at the output layer, so second stage, and at the ith neuron. So this is a quantity that is defined at the ith output neuron like this. So you imagine that it is available at the output neuron just as this is available, this is available, this is available, this is also available at the ith output neuron. Now, once you have the deltas at the ith output neuron, you calculate the deltas at the hidden layer by back propagating these deltas. Sorry, I'm getting these stray lines. I don't know why. I don't know how to get rid of them, but sorry about that. So this is ith and this is jth. So you have deltas available at the output, delta I is. Now using them, you back propagate these deltas to the hidden layer. So this is hidden, all right, and calculate the deltas at the jth hidden neuron using this formula. So delta j first, I'll call it first, is equal to sigma delta I second times wij second. Okay, so this is summed over. So basically you are summing, or you take the deltas, pass them through the weights in the reverse direction, because weights you imagine are taking information in the reverse direction. forward direction. But as far as the delta calculation is concerned, weights are used in the reverse direction. And you also multiply them with G prime Hj of f. So Hj of f is available, is the total input going into this neuron. So you use that here also. So you define two such quantities. These are like deltas. Now we plug in these deltas into the previous equations and some magic happens. Let us see what it is. So if you look at the first equation, delta W ij second stage equal to eta. So this has di minus yi times g prime hi of s. And that is nothing but the delta at the second stage. So you directly plug in there and multiply it by Vj. Only Vj is left. Okay, so you get a very compact, cute expression for the first stage, for the second stage. So similarly, if you take delta jk first stage, you get, so if you take this whole expression, so you get actually, if you minus sign, if you get it off, you get eta times, right, sigma I di minus yi times g prime of hi of s times w ij of s times g prime j of f times x. So this is a whole expression. Now in this expression, if you plug in these deltas, so up to this point, you get, so this is equal to eta times sigma I times, this is delta I of s, okay, multiplied by wij s, right, this whole thing. So this goes into brackets because this is index is j. We don't need to put it inside this summation. So g prime j of f times xk. Now this expression, as you can see, is nothing but delta j of jf. So is equal to delta jf times xk. So thing is, in the earlier version, the learning rule was satisfying locality principle at the output layer, but still slightly complicated, which is okay, but it satisfies learning rule. But the learning rule for the second weights, that's the first stage weights, is pretty complicated and doesn't satisfy the locality principle. So locality principle, right, it violates. Okay, so, but if you look at this form, so basically you imagine that the weight wij of second stage, right, has something like delta si at the output and vj at the input. Now update of this weight is nothing but product of this and this. Okay, so similarly, if you take the first stage weights w jk f, so we have this new thing called delta j f available at this end of this weight, and input here is xk. Update for this is product of these two. So which is what we have done here, which is what we have done here. Right, so this is the expression. Now, so up to this part, it is satisfying locality principle. But point is, we're able to achieve locality by invoking these new quantities, deltas. But what about the computation of deltas? Does it satisfy the locality principle? So let us look at that. So delta computation for delta is at for the output layer is simply di minus yi times g prime hsi. So this is available at the ith output neuron. This is also available at the ith output neuron. So this is totally cool. I mean, there's no problem with this calculation. Now let us look at the delta fj, which is calculated at the jth hidden neuron. To compute this, we are taking inputs from these neurons. So this is available at the jth hidden neuron. To compute something that is occurring here, we take inputs coming from this connection and all these connections, which is okay because this is actually connected to all these connections. right? And so therefore, this is also satisfying locality principle. This satisfies locality principle. This also does. This also does, and this also does. So basically, by invoking these intermediate terms called deltas, you are able to transform the entire learning algorithm, all the learning equations, in such a way that they satisfy the locality principle. So that is the beauty of this algorithm, and this is called the backprop algorithm. So anyway, I've tried to work it out, so that it's easier to follow. But we have the equations given here. So basic summary of the whole thing is, at any given level, any connection is simply updated. So if you have Wij, right, you take the delta at the output layer and Vj at the state at the input layer, the previous layer, and multiply these two. So delta Wij is equal to beta times delta at the output times state at the input of that connection. So this is very general, right? And no matter how complicated your network is, ultimately your weight update will have this form, which is quite beautiful. So this is the backprop learning algorithm. So the way it works is, so it applies for a network of any size. We have worked it out for one hidden layer, but same thing can be generalized to a network of any number of hidden layers. So here, this is the input, then it goes through a bunch of layers, and this is output Y, right? This is called a forward pass. Okay, and once you in the forward pass, at the end of it, you find output Y. Then compare the output by, with the desired output or the target output, right? We've been using notation D minus Y. Right. And so then calculate deltas here. So at the output layer, and then using that, using the error here, the deltas here, you backpropagate them and calculate the deltas all the way up to the first hidden layer. You don't calculate deltas at the input layer because it doesn't have any meaning. Right. So you calculate deltas at all the hidden layers and including the output layer. Then once you do that, all the weights are updated in one shot by using this general scheme. Like I said just before, the delta at the output end of the weight times Vj, the state of the input end of the weight, multiply these two with a step size, right? You get the update. Okay, so same thing you can do for any number of hidden layers. And one more point I want to mention here is how to handle these thresholds, right? The bias terms, we are using notation theta here. So basically here the idea is, if you take a given neuron, right, which has a theta value and some inputs x1, xi, and xn, output is y. Okay, so what happens is y is equal to g of sigma wi xi minus theta. Okay, so the same thing you can write as y is equal to g of sigma wi xi. So here the summation goes from I equal to 1 to n, right? And now imagine that the summation goes from I equal to 1 to n plus 1. Okay, so where x of I plus 1, sorry, n plus 1, the last output, right, is equal to minus 1, and w of n plus 1 is equal to theta. So basically you think of this weight as having the value theta, and input to that is minus 1. Okay, so if you think of this as the bias as another input, okay, where the input to that is minus 1 multiplied by theta, so this whole thing is absorbed into this summation, right, by treating this as minus 1 and taking it as a plus. So then you have one more term, the n plus 1 term. Okay, you will have an expression like this. So after that, you can absorb it into the other equations, and you will have the math looks a lot more uniform. Okay, you don't have to treat the bias term as a special category. Okay, so that's why I didn't use the bias term in my derivation. But if you just use this kind of an assumption or a notation, right, bias also becomes like one more term. And then if you want at the end, if you want to expand it out and actually write it separately with a different notation, right, you can write it like this. Okay, so now that explains how to derive the learning rule, right? So how do you use this network? So basically what happens is if you want to use a network, you want to train it on some data set. You take the data set, now take the network, randomly initialize the weights, then train the network using the backprop equations that we just described, and keep on training it until the error goes to a very low value. So because the objective of training is to achieve ultimately zero error, but some kind of minimum error. So you keep training until the error goes to minimum. Once the network is trained, you freeze the weights and then start using network on new data set, on a new data set. Okay, so there's some merits to this whole approach. First thing that I want to mention is that we call this the whole neural network approach to problem solving, because in the traditional approach, which is algorithmic approach, to solve a problem, by problem solving, what I mean is like you transform a bunch of numbers into another bunch of numbers. Okay, in algorithmic approach, the transformation is done by following a set of predefined definite steps, and which you have to figure out by analyzing the problem. Right, you have to have domain knowledge, and you have to analyze and come up with a set of rules all by yourself. Whereas in the neural network approach, you don't have to do that. You just take a lot of example data, right, from that problem, and then you train the network. Network will learn a mapping, but you don't ask what the network is doing. It is acting like a black box which maps an input vector onto some output vector. But the beauty of it is it's a general solution to a large class of problems. Right? You want to, for example, classify. You want to be able to read text. Okay, give text image as input and some kind of ASCII code or something like that as output. And train the network. Or you want to, like Alexa, right? You want to train a network which can understand speech. Give speech as input, and the output will be some kind of a text, right? Text code, right? ASCII code or something. It will just learn the mapping. So, or you want to understand somebody's sign language. Somebody is gesticulating and producing signs. You can understand signs. So give that whole video to another network, and then it will convert them into some kind of words or something like that, and you get the output. So the thing is, traditionally, to solve any of these problems, you'll have to analyze, how to break up the speech samples, speech signal, and then where are the vowels, where are the consonants, what is the envelope, what are some capstral, parameters, and all sorts of things. Right? So now you just give the input to the network, it will learn and give you the output. I mean, I'm making it quite simple. I mean, oversimplifying it, but that's the beauty of this whole approach. It is a general solution approach to a large class of problems. And we also know that because one doubt you can have is what is the guarantee that the network will learn the task? You can throw lots of data at it, but what's the guarantee it will learn? Now, the approximation theorem says that even an MLP with a single hidden layer, as long as there are enough number of hidden neurons, it can learn almost any practical function, real world function. The major assumption is that the function has to be continuous. Okay, if that is given, and obviously in real world data, you will be looking at the function over a finite domain. Okay, you don't want to learn it from minus infinity to plus infinity. So only these two conditions are required by the approximation theorem. And they're pretty reasonable. So you can be sure that in principle, that there exists a solution, right, which gives you a great accuracy for the given problem, for a given function. Now, the backprop algorithm is also quite beautiful. It applies for arbitrary number of layers and even partial connectivity and so on and so forth. The only requirement is it should not have loops. So basically, we have done the derivation for a network with just 3 hidden layers. Okay, so the input, hidden, so the output, hidden, and input. But like I mentioned, it is valid for a network of any number of hidden layers. That's why the same algorithm can be used for deep networks also, which we'll come to later. But not only that, it is valid for even much broader class of problems. Like, suppose I give input here and this goes to the output, and then I have a bunch of layers coming in here and another input here, given here, and then, all right, and this actually will jump over this and also send another set of signals. Right? Point is, yeah, all these are the come under the broad category of what is called feed forward network. There's no feedback, there are no loops. For example, this is not a loop because these are two parallel lines, two parallel pathways. That's not a loop. Loop means you have to go and come back this way. And such networks also exist, but the backprop algorithm doesn't apply to that. They have different set of learning algorithms. They can also be trained. But what I'm saying is the backprop algorithm can apply to a wide class of networks called the feed-forward networks. And another thing which we have again time and again emphasized is that it satisfies the locality principle. So once you have locality principle, all the computations are occurring as if they are occurring over a physical substrate. That means imagine that there are real neurons there exchanging information, sending information out, taking information in, and there are real connections, right, transmitting information over themselves. So if you think of the network as a physical network like that, then all information has to be accessed locally. And a connection can only get information that is available at its two ends. If you have a connection like this can read information available here and available here. It can't get information available here. Okay, so similarly, a given neuron has information coming from its input connections, right? And that's the only thing it has access to. Okay, so once all the computation networks satisfy this property, you can put this network on a parallel machine, on a parallel computer, where each neuron is a separate processor. Ultimately, you can do that, and that way you can get great speed ups, right, in the whole computation. And there's a lot of dedicated hardware for neural networks, parallel hardware. Now people are putting it on GPUs, but it is possible to really, in principle, parallelize neural networks because of this property. So in fact, way back in the 90s, when neural networks were just becoming popular, people have developed, there's a company called, it was a machine called Connection Machine, which had 64,000 processors. It was one of the largest parallel computer at that time. So using that, you can do very fast parallel computations. So the intrinsic parallelism of the neural network lends itself naturally to be ported onto parallel machines. Then the hidden neurons act as feature detectors. Okay, so we'll talk a little bit more about this later. But point is, if you look at traditional pattern recognition algorithms, right? Let us say you want to recognize speech. You take the speech data and extract a lot of features, right? And then you better be good at those features that you have extracted, that you are computing, and then give that to some kind of a classifier, and it classifies it. So a lot of thinking and analysis goes into extracting or defining ideal or optimal features. But whereas with the neural network, you can give pretty much the raw data, but the hidden layer neurons work like feature detectors. And sometimes if you analyze what the hidden network is, the hidden layers are doing, they seem to be detecting some really intelligent features. So they do that work, your work for you. You don't have to sit and analyze and come up with the really smart features. Okay, so this and another thing is this kind of an approach is good when no model is available. So you're trying to map an input X onto an output Y. So this is your MLP. Okay, and you don't have a mathematical model to connect these two because we don't understand underlying physics or something like that. But we know that these two are related. Then you can always just train an MLP. You don't have to worry about the math that you haven't worked out. So these are some of the advantages of an MLP. Obviously, there are also disadvantages and some complaints and criticisms about the way the neural network works. The first complaint that's been there for quite a long time, and actually it's not a major complaint. You can go around it and make it not look as bad as what was originally believed to be. Is that the network acts like a black box, because if you see what we are doing, we have an MLP, and then input is given. You have a bunch of hidden layers inside, and you get the output like magic. Okay, so input and output. We don't know what is happening inside. Right? Whereas if you look at any algorithm, suppose you are doing a sorting algorithm. right? Input is one set of numbers, unsorted. Output is a sorted set of numbers. You know exactly how the sorting is done at every step. It's not magic, right? Suppose somebody says, "I have a black box," it will give you sorted data, right? And then, but you can't explain how it works. You won't be sure of it. I mean, next time when you give a set of numbers for sorting, you don't know, you're not sure if it gives you correct answer. So that is what happens, and then that's why I think people talk about as a black box, right? But actually, it is not that bad, because what happens is when you train a network on some data and actually go into the network and analyze the response of the hidden neurons, you will find that it is doing something quite intelligent very often, right? But people don't usually take the trouble to do that analysis. So, for example, we'll look at some deep learning examples later. So, deep networks trained on visual pattern recognition problems. I've found that the lower layer neurons, pick up some primitive image features, like edges and like simple oriented bars and things like that. And as you go higher and higher up, the neurons seem to detect and respond to more and more complex features of the input image. There is a very logical assemblage, right, of features starting from very low scale local features to larger and larger scales, patterns, right, available in the image. So if you do the analysis, you can see this kind of a patterning happening inside the network. In fact, this kind of a breakup of the problem which the neural network does on its own, right? It looks a lot like how brain itself breaks up the problem, right? And so gradually assembles patterns to larger and larger scales and recognizes the whole pattern. So those comparisons we'll do later over the next few classes. So although there is some point in this black box complaint about how a neural network works, I want to say it's not that bad if you take the trouble to analyze how the network is solving the problem. Now, limits of generalization are not clear. We'll talk a little bit of that later on, because the problem is the network is basically doing a regression. It's a regression engine, right? It's just learning to curve fit, right, the input data and the output data. So it is not clear what happens sometimes when you give data which is outside the range of the input data. So I will talk a little bit about that later. Now, it's hard to incorporate prior knowledge. Sometimes, right, there are aspects of the problem that you know and you understand, and you would like to help the network. That is, you want to help give the network a head start, saying that I don't know how to solve this problem in its entirety, but I know this part of the problem is understood, and we should know this. So for example, right, let us say I'm trying to recognize characters, alphabets. Okay, so this is A and this is B and so on and so forth. So network has to take this as input and give some kind of this neural network, and to give some kind of a code. Let's say A is this is a code for A, some 1 or something like that, and for code for B is 2 or class 2 or something like that. Now, thing is, input is an image, output is a code, a vector or something like that. Now, we know that when A is shown, right, no matter where A is shown in this box, it's the same A, whether it's centered or to a side, or it could be large A, it could be small A, they're all A's, right? That we know. So the network should have the properties of translation invariance. That means no matter where your input image is inside the box, it's the same class. And another thing is scale invariance. No matter what size it is, it's the same class. So now, how do you tell the network this concept? Right? There's no easy way to just incorporate this into the connections of the network. The brute force way would be to give a lot of examples, right, where A is placed in different parts of this box, and you keep telling the network, look, all of them, they look apparently different, but they're all the same character A. So map it onto the same thing. Similarly, the scales. But that's a laborious way of doing it. Maybe if you show this over and over with many different characters, it will learn the underlying concept that the location doesn't matter, only the shape matters. I mean, it's possible for the network to learn something like that, but it's a very laborious kind of thing. Simply there's a basic property that this algorithm should have, but there's no simple way of teaching it other than this brute force method. This is a problem. You can get around this to some extent in artificial systems, but it is still a problem. Another problem is it is slow in training, right? Because usually if you want to learn the train network on a large data set, you have to have a large network, right? Sometimes running into millions of connections. And to train that takes time. And so now that you have fast computers, lots of cores, and it's still not a problem, but it is in principle a problem. Once it is trained, it is very fast because training is an iterative process, as you have seen, right? And so therefore, it takes like thousands of epochs to train the network sometimes. But once it is trained, testing is pretty rapid. That's why the networks are used in all sorts of your Alexa or your driverless cars. They all use deep networks because they're very fast once they are trained. So another problem is problem of local minima. So if you see how we are training it, you take your error, right, which is a function of all your weights. So I'll just say Wi, but you can have a million weights. This is one of the weight components. The error is a complicated function of the weights because we are trying to find minimum, but the error can have many minima. And some of them are very low. So if you are able to go here, you get a great solution. But where you go depends on your initial condition. Since the network is doing only gradient descent, if you start from here, you will just roll down to the nearest minimum and stop there. Okay, so if you start from here, roll to the nearest minimum and stop there. Okay, so if you want to get to this point, which is called the global minimum, right, you should be lucky enough to have started somewhere from this neighborhood, right? Then you'll land here, but there's no guarantee that you have started from here because you're initializing weights randomly. You could be anywhere in the whole state space. Okay, so this is a problem. So you get stuck in local minima. But the good news is, although the local minima problem is a real problem, the network space is very rich. It's like very complex. So let me give an idea. Give you an idea. Suppose I have a network with n hidden neurons, single output y and single input x. Okay, and so this is x. Now, so let us say you have trained this network and you got some weights and you got one solution. And that happens to be local minimum. Now you can see that if you think of this network as a physical network, where these neurons are physical nodes and these connections are physical connections, you think of them as some kind of beads. These are beads and these are threads connecting the beads. And now you just permute the beads, right? When you move the beads among these locations, imagine that the threads also will move along with the beads. So then what you will notice is, if you have n neurons or n beads here, you can have n factorial total permutations. Okay, you will have n factorial permutations. That means every permutation represents one network because it represents one set of weights. And but we know that every such permutation gives you identical network because it's a sum of the same things. So basically, sum of certain quantities. And if you jumble the quantities, the order in which they appear in the summation, it's still the same summation. Okay, so but in terms of the weight space, it's a whole different network. Every permutation represents a whole different network, different point in the weight space. So what that means is, for every network, right, that you have with a set of weight values, there will be n factorial minus one other networks, right, in this weight space, which are identical, right? So if you have 100 vectors, 100 weights in the weight space, this is a pretty huge quantity, right? So point is, although the problem of local minima is real, right? The weight space is so complex, and you can have many solutions which are totally equivalent. Okay, so even if you miss one local minima, you can get something else which is probably equally good. Okay, so it's not a real problem, and especially these days, I know if you just take a large network and put it on a big computer, you'll always find some reasonable solution. Okay, so that is some basic understanding about the advantages and demerits of an MLP. Now, when it comes to developing an application, so this is, I'm talking more from an artificial application point of view, but we can also relate to it from the point of view of brain models. So it has these following stages. So you have, first you do a feasibility study, then you collect data, right, and you design and train the network, and then test the network, and then finally deploy the network in real usage. What is this feasibility study? Right. First, you need to figure out, ask yourselves, do you need an NN? Do you need a neural network? Right? Because what that means is, in a neural network, you are trying to map input data X, okay, which is in some n-dimensional space, onto an output data Y, which is in m-dimensional space. You're trying to find a mapping. This is what network tries to do. But what if this mapping is so simple, I can just get it by multiplying with a matrix? Maybe just linear transformation is good enough for doing the mapping. Then why do you need this nonlinear model called a neural network? You need to make sure that the problem is complex enough that it warrants use of a neural network. So that's the first thing. Then is it an input-output problem? Is it simply a question of mapping one input onto an output? And can you represent those inputs and outputs as vectors? Because a network only understands vectors. So even if are doing image processing, image pattern recognition, you have to ultimately convert that image into a vector. Or you're doing speech recognition, you have to convert that into a vector. So you need to make sure that you can convert your problem into input-output problem, and you can express your inputs and outputs as vectors of a fixed dimension, and then you can talk about network application. You should be able to define the inputs and outputs very clearly. And are they, the inputs and outputs, even uniquely related? Even physically, does it even make sense to link these two? For example, if you want to build a neural network model relating the sunspot activity with Infosys stocks or something like that, it doesn't make any sense. They're physically unrelated. So you can take some data from both these sources and crunch some network, and you'll get some performance. You can write papers also about that. But it's stupid. It doesn't make any sense. So you need to first have some basic understanding of the processes that you're trying to model, and you should be reasonably sure that the two things that you're trying to learn to map are physically related, and then you go ahead and build a model. Then do you also have enough domain knowledge, and do you have enough data? So domain knowledge, people think that because your network is like a black box, I put some garbage in, garbage out, right, and it will take care of itself. No, that doesn't work that way. You need to make sure that it is meaningful to build a model between these two. And sometimes, even though a network can learn any continuous function over a finite domain and all that, it may not be desirable to just train one big, jumbo network on the data, because the approximation theorem only assures existence of a solution. It doesn't assure that if you use backprop algorithm, it will get you that solution, right? Because there could be practical limitations. We have seen some of the practical limitations of backprop. Okay, so in such situation, maybe you want to break up the big problem into lots of small problems, right, and create and use a whole set of neural networks, right, to come up with a complete solution. So to do all this, you need domain knowledge, and that kind of understanding is also necessary if you are thinking of using this kind of neural networks for as and propose them as models of brain function. So we look at some of those things in the next class. So let us stop here, and if you have any questions, I can take the questions. Any questions?